Hi everyone. So today we are going to talk about trigonometry of right triangles. So before we jump into some actual problems, we're going to go ahead and define a couple of key vocabulary words when it comes to right triangles. So specifically, we look at theta, which is always our reference angle. It helps us determine which side is opposite versus adjacent. So those are our next two pieces of vocabulary. Opposite and adjacent are both legs of a right triangle. So legs are the two sides of a right triangle that touch or are adjacent to the 90-degree angle. So the leg that is opposite the reference angle, we call the opposite leg. And the leg that touches the reference angle we call adjacent. And the last side of a right triangle, which happens to be the longest side, is the hypotenuse. We'll go ahead and do that in orange. Hypotenuse. So we can use these different labels on a right triangle to come up with different trig ratios of this particular reference angle. So if you are looking for sine of theta, what you want to do is find the ratio of the opposite leg and divide it by the length of the hypotenuse. Okay, now cosecant is just the reciprocal of sine. So we're going to take that ratio and we're going to flip it. So instead it's going to be hypotenuse over opposite. Okay, cosine, instead of using that opposite leg, you're going to use the adjacent leg. But it's over the hypotenuse. And then once again, secant is the reciprocal of cosine. So you're just going to flip that ratio. It's going to be hypotenuse over adjacent. Okay, and then tangent, that's a ratio of the legs only. Tangent of theta would be your opposite leg over the adjacent leg, which would mean cotangent is just the reciprocal of that. It's going to be adjacent over opposite. Okay, so in number one, what we're going to do is find all of the 6 trig ratios given the particular triangle. So for this type of problem, we need to know all 3 side lengths. We're only given 2, but if you remember, if you know 2 sides of a right triangle, you can always find the third by utilizing Pythagorean theorem. And so that's what we're going to do next. So Pythagorean theorem is leg squared, which is 6 squared, plus your other leg squared. We don't know it, so I'm going to call it b. And that equals your hypotenuse 10 squared, or a squared plus b squared equals c squared. 6 squared is 36, plus b squared equals 10 squared, which is 100. Okay, then we're going to go ahead and subtract 36 from both sides. We end up with b squared equals, this is pretty nice, we get 64. Square root both sides, and b equals, now be careful, technically it's plus or minus 8. We'll get into why the plus or minus is important in a future lesson. It actually depends on what quadrant theta is and all kinds of stuff. But for right now, we're just going to use the positive 8 for b. Okay, sine is opposite over hypotenuse. So remember, opposite is the leg that is not touching the reference angle. So this one is the opposite, which would make this one the adjacent, and 10 is your hypotenuse. Okay, so sine is opposite, which is 6, over your hypotenuse, which is 10. We're going to go ahead and reduce that as well. So 6 divided by 2 is 3, 10 divided by 2 is 5. Remember, cosecant is just the reciprocal, so I can take this and just flip it. So we end up with 5/3. Cosine now is adjacent over hypotenuse. Adjacent is 8 over hypotenuse, which is 10. This reduces to 4 over 5. Remember, secant is just the reciprocal of cosine. We're going to go ahead and flip it to 5/4. And last but not least, we're going to do tangent and cotangent. Tangent is opposite, which is 6, over adjacent, which is 8. That reduces to 3 over 4. And then remember, for cotangent of theta, we take the reciprocal of tangent to get 4/3. Okay, go ahead and use that exact same idea. You're going to pause here, do number 2, and then we'll go over it together. This one's a little bit more tricky because there's an alpha and a theta. They try to throw you off by changing up the reference angles, so just be careful. All right, so hopefully you've had a chance to go ahead and do that. It looks like number 2, the hypotenuse is missing, so we want to solve for that first. We have 2 squared plus 3 squared equals our hypotenuse, c squared. We don't know what c is. So we have 4 plus 9 equals c squared. 13 equals c squared, square root both sides, and c equals plus or minus root 13. But remember, for the purposes of these problems, we're going to use the positive root 13. Okay, sine of alpha. Whenever it's alpha, this guy right here is my reference angle. So be incredibly careful with that. Sine is opposite over hypotenuse. So here we want to use the side opposite of alpha, which is 3 over hypotenuse, which is root 13. Now the last thing I want us to do is rationalize the denominator. So we can multiply this by root 13 over root 13, and my final answer is 3 root 13 over 13. Okay, now if I flip actually the original version of this, the 3 over root 13, you actually end up with root 13 over 3, and you don't have to rationalize it. If you were to flip the 3 root 13 over 13, you'd have to rationalize it. You'd still get this as your answer. It's just some extra steps. Oh, actually, I just realized they switched up our reference angle on us. So actually, we can't just flip it in this case. We need to actually pay more attention than that. That's why I even color-coded that alpha in the first place. So now actually I'm going to do this in red. Disregard that. We can't just flip it because guess what? We're now using theta as our reference angle. So be careful. Don't do what I just did. So cosecant, remember, is the reciprocal of sine. So instead of opposite over hypotenuse, I want the hypotenuse over whatever is opposite of it. So hypotenuse is root 13. Now, opposite of theta is actually 2. So you end up with root 13 over 2, not 3. So be careful. Okay, cosine of now theta. So I'm actually going to go through and just color code this so I don't do that again to make sure my brain is thinking about these correctly. Okay, so cosine of theta is adjacent over hypotenuse. So adjacent to theta is right here, right? So adjacent is 3 over hypotenuse is root 13. It's actually equivalent to sine of alpha. You end up with 3 root 13 over 13 when you rationalize. Okay, secant is the reciprocal of cosine, so it's going to be hypotenuse, which is root 13 over adjacent. Now we want adjacent to alpha is actually 2. Okay. All right, tangent of alpha, we went opposite over adjacent. Opposite of alpha is 3, and adjacent to alpha is 2, so 3 over 2. Cotangent of theta, we want to flip it, right? So instead of opposite over adjacent, it's going to be adjacent over opposite. Well, adjacent to theta is 3, over opposite of theta is 2, right? There's a lot of similarities here. There's a relationship between alpha and theta for sure when it comes to those trig ratios. So learn from my little mistake there. Always pay attention to what reference angle it's using, because that does completely change your answer that you end up getting. All right, let's move on to number 3. So it says if cosine of theta equals 3/4, sketch a right triangle with acute angle theta and find the other 5 trig ratios of theta. So this is what we call a reference triangle. I'm going to go ahead and just draw a generic right triangle. And you can put theta in whichever spot you want. Make sure you have that 90 there because that is important. It is a right triangle. So we have theta, which I can throw right here. And cosine of theta is a trig ratio where we have adjacent over hypotenuse. So this means your adjacent leg is 3 and your hypotenuse is 4, but we actually don't know the opposite leg. So we're going to have to find that. So we can use Pythagorean theorem. 3 squared plus, we'll call this b, I guess. B squared is equal to 4 squared. So we end up with 9 plus b squared equals 16. Subtract 9 from both sides. We end up with b squared equals 7. We can go ahead and take the square root of both sides. And b equals plus or minus root 7. Now remember, we want to use the positive root 7 here. Okay, so we already know that cosine of theta is equal to 3/4. So let's go ahead and find secant of theta, because that's nice and easy. We just flip it. We get 4/3. We still need to find sine of theta, cosecant of theta, tangent of theta, and cotangent of theta. All right, so sine is opposite over hypotenuse. So opposite of theta, remember if I can draw an arrow to that leg, we get root 7 over 4 is our hypotenuse. And then we want to flip it for cosecant. So we get 4 over root 7, but we want to rationalize that. So we end up with 4 root 7 over 7. Tangent of theta is opposite of theta is root 7 over adjacent, which is 3. Cotangent, we just flip it. So we get 3 over root 7. We rationalize that. You should get 3 root 7 over 7. Okay, so now that we've been able to use these triangles to find right triangle trig ratios, let's go ahead and move on to some special right triangles. So we have 2 special right triangles with some rules, 45, 45, 90, and 30, 60, 90 triangles. 45, 45, 90, these have a specific name. These are isosceles right triangles, because if one leg is x, so is the other leg. The legs are equivalent. And there's a rule to help you find the third side, which would be x times the square root of 2. Now, where that comes from is actually Pythagorean theorem. So if one leg is x, we have x squared plus another x squared, a squared plus b squared equals c squared, right? C is the hypotenuse. This is 2x squared equals c squared. You square root both sides, and c would then equal x root 2, well, plus or minus, right? But that can kind of be taken into account with the x in front, plus or minus, right? But we use the positive x root 2. Okay, so 45, 45, 90 triangle rule. Both legs are equivalent. Take the length of the leg, multiply it by root 2, and you get the hypotenuse. Okay, the next rule is for 30, 60, 90 triangles. We always start with the shortest leg, which is the leg opposite of 30 degrees. That's our x. To get the longer leg, you take x and you actually multiply it by √3. So the leg opposite of 60 degrees is x √3. And then your hypotenuse, we just double the length of the shorter leg. So this problem is really easy if they give you the leg opposite of 30 degrees. It's not too bad if you have any of the other sides either, but that makes it really, really easy when they do that. Okay, so let's go ahead and jump into some problems. Number 1, we have a 45, 45, 90. We're given one of the legs is 3, which means the other leg also has to be 3. Now, if you remember that rule, you know you don't need to use Pythagorean theorem. We know that to get the third leg, or the third side, we take the leg and multiply it by √2. So 3 √2 is your hypotenuse, and you're done. Super easy if you know that rule. Okay, let's look at number 2. We have a 30, 60, 90. We're given the side opposite of 30 degrees, which is great for us. That's the one we like to start with. That's our x. We double it, right, to get our hypotenuse, and we multiply it by √3 to get that leg. So this leg is just 4 √3, and the hypotenuse is double 4, which is just 8. Okay. All right, now this one, number 3, we have a 30, 60, 90 triangle with a hypotenuse of 16. Be careful, we start with the shorter leg, the leg opposite of x, which means they actually gave us our hypotenuse, which is 2x. So 2x equals 16, but we can very easily divide by 2 and get that x equals 8. And now we just multiply the shorter leg by √3, we get 8 √3 to get the longer leg. Okay, go ahead and pause the video here, do 4, 5, and 6 on your own, and then I will go through it with you. Okay, let's look at number 4. So remember, 45, 45, 90 triangles. They're giving us the hypotenuse. Remember, we start with the legs, which are always equivalent, x and x. And then we multiply x by √2 to get the hypotenuse. So we can work backwards. 5 √2 equals x √2. If I divide both sides by √2, we end up with x equals 5. So both your legs are just 5 in length. Okay. All right. Number 5, we have another 45, 45, 90. Very similar. Both legs are x. The hypotenuse is x √2. So if we know that 6 is equal to x √2, we can divide by √2. X equals 6 divided by √2. Let's go ahead and rationalize that just to make it cleaner. Multiply by √2 over √2. X equals 6 √2 over 2. Well, 6 divided by 2 is just 3. So x equals 3 √2. Okay, not too bad. Very similar to number 4. Number 6, remember, this is a 30, 60, 90 triangle. We always start with the shortest leg is x. The longer leg is x √3, and the hypotenuse is 2x. So if I know that 12 is equal to x √3, we can divide by √3 to find x. X equals 12 over √3. Let's go ahead and rationalize to make it a little nicer. X equals, 12 √3 over 3. 12 divided by 3 is 4 √3. So x equals 4 √3. And remember, we just double it to find the hypotenuse, which is 8 √3. So not too bad. Okay, that was a little overview of our special right triangles. The very last thing that we're going to do is use different theorems, whether they are the triangle angle sum theorem, trigonometry, or our special right triangle rules to figure out missing side lengths and angle measures of right triangles. So first of all, I ask a student to solve a triangle, what that means is I want you to solve for anything that's missing, any missing angles, any missing sides. I don't just want you to solve for one side or one angle. There's probably multiple components to the problem. Like I just stated, there's a few different tools you may have to use. Trigonometry, special right triangle rules, triangle angle sum theorem. That just states that the sum of the angles in a triangle is 180 degrees. You might remember that from geometry. All right, let's look at some examples. So number one, we're solving the triangle. So if you might notice that this is actually a 30, 60, 90 triangle. It has to be 60 degrees because 30 plus 60 is 90, plus that 90-degree angle, we get 180 degrees, which actually makes this problem a lot easier to solve. So far, we already found angle B. So the way we write this is the measure of angle B equals 60 degrees. Okay, now we need to solve for A, lowercase a, and B still. We're given the hypotenuse, which is always 2x. Remember, A is your x, right? And B is your x root 3 in this case. 2x equals 12. Well, if I divide both sides by 2, I get x equals 6, which means that A is equal to 6. To find B, we just take A and multiply it by root 3, so we just get 6 root 3. So that did not require any trig because it was a special right triangle. Now, would you get different answers if you used trig? No, but you wouldn't be able to get the exact answer for B. You'd probably get a decimal that's still equivalent. Okay, let's take a look at number 2. We are only given one angle measure and one side. This is also not labeled, so if a triangle is ever not labeled, go ahead and take a moment and label it A, B, C, okay? All right, so we know angle B, or angle A, and angle B, I guess because it's a right triangle, they gave us two angles, but only one of the acute angles. So we still need to find C. We can find that by using triangle angle sum. So 90 degrees plus 75 degrees plus the measure of angle C should add up to 180 degrees. Subtract 90, we get 75 degrees plus the measure of angle C equals 90 degrees. Subtract 75 from 90, and we get the measure of angle C is equal to, let's see, 15 degrees. Small little angle. I'm going to go ahead and label that on there. Okay, the next thing we need to find is the length of AB as well as the length of AC. Now what you can do, and actually this is common geometric notation, is the side that's opposite of angle B you can label as lowercase b, and the side opposite of angle C you can use lowercase c. Okay, so let's go ahead and use we're gonna have to use some trig, it looks like, to solve for B and C. All right, so we're given A is 75 degrees. I'm just gonna use that as my reference angle. Okay, so I know the leg that is opposite of 75 is 100. If I'm solving for B, I want the hypotenuse. So think, what trig ratio uses opposite and hypotenuse? Well, turns out that it's sine. So we have sine of 75 degrees equals opposite, which is 100, over your hypotenuse, which we're solving for is B. Multiply both sides by B, we get B times sine of 75 degrees equals 100. Divide by sine of 75 degrees. And B is approximately, so the exact answer is 100 divided by sine of 75 degrees. We're gonna use a calculator and get a decimal. It looks like you get approximately 103.528. Be careful, make sure your calculator is in degree mode for this because you're using degrees. Okay, to solve for C, that's an adjacent side. We also know the opposite leg, so let's go ahead and use tangent. So tangent of 75 equals opposite, which is 100, over adjacent, which is c. We don't know it. We're going to multiply both sides by c. So we have c times tangent of 75 equals 100. Divide by tangent of 75 degrees. And c is approximately, what do we get? 26.795. Okay. All right, the last one, go ahead and pause and try to do this one on your own. Be careful, your calculator needs to be in radian mode for this one. So just make sure your calculator's in radian mode. And then once you've done it, unpause and we'll go through it together. Okay, so hopefully you had a chance to do that. We're gonna do this last one together. And so the first thing that we can do is we can go ahead and solve for that missing angle. We're gonna keep it in radian form. And let's go ahead and we'll go ahead and label this A, B, C. It just makes it a little easier. This would be lowercase c, lowercase a. Okay, now what I do know is that a triangle adds up to 180 degrees, which is equivalent to pi radians. So you can think of this as, right, pi over 2 is 90 degrees. Well, we know that 3 pi over 8 and the measure of angle A has to add up to pi over 2. So measure of angle A plus 3 pi over 8 should equal pi over 2, right? Otherwise, it would break our triangle angle sum rule. One way you can do this is rewrite the pi over 2 with a common denominator. So we have measure of angle A plus 3 pi over 8 is equal to 4 pi over 8. Subtract 3 pi over 8. And the measure of angle A is equal to pi over 8 radians, right? We're going to leave the angles in exact form. Okay, well, now we need to solve for both lowercase a and c. Those are side lengths. We're going to have to use some trig. I always like to use the angle given just in case I made a mistake of finding the other angle. But it's up to you. You could use pi over 8 as well as your reference angle. All right, let's start with finding A. So A is the adjacent leg. We're given the hypotenuse. So it looks like we want to use cosine of 3 pi over 8 equals adjacent, which would be lowercase a, over hypotenuse, which is 425. We're going to go ahead and multiply both sides by 425. The exact answer is 425 cosine of 3 pi over 8. But if we punch that into a calculator, let's see, we get about 392.649. All right, so we also need to find C, which is opposite to 3 pi over 8. We're given the hypotenuse, so we're going to actually use sine for this one. Make sure, sorry, if you didn't get the same answer as me for that 425 cosine of 3 pi over 8. Oh, whoops, I had that flip-flopped on my key. Sorry, you shouldn't have gotten that as your answer. You should have gotten 162.640. That's me trying to save time, not punching that into a calculator for you guys. 162.640. But if you didn't get either of those answers for A or C, you probably were in degree mode still, so don't forget to switch your calculator back over to radians. To do that, you hit second mode, and then you should be able to go down and hit select radians instead of degrees. Okay, so sine of 3 pi over 8 equals opposite, which is C, over hypotenuse, which is 425. Multiply both sides by 425, and C equals 425 sine of 3 pi over 8. Punch that into a calculator. I'll read the right one this time. We get approximately 392.649. Another good thing to do to avoid maybe the error that I almost made is remember that the side opposite from a larger angle should be bigger. So like, for example, C should be larger than A because C is opposite of 3 pi over 8, whereas A is opposite of pi over 8. So just be really careful with that. It's a good way to double check your work. Okay, thank you for watching. That is it for today.